Hi everyone, welcome to this class where we are going to look at the first law of thermodynamics. So in the previous class we had looked at the zeroth law. This class we are going to look at the first law of thermodynamics and also specific heats of a gas. I'm going to make all these thermody concepts absolutely crystal clear for you. So let's go ahead and get started. Before we begin, just a quick reminder, do check out the other courses on our website, manochaacademy.com, and our Android app. All the links are given below. As you know, we have courses on physics, chemistry, biology, maths, coding, and artificial intelligence. In our courses, you're going to get live classes, concept videos, quizzes, questions, mock test, and revision notes. So guys, do check it out. All the links are given below. So what is thermodynamics? You guys remember from last time? In thermodynamics, we are dealing with the relationship between heat, energy, and work. And here we'll talk about the concept of internal energy. We are looking at how energy is transferred and transformed in these physical systems. And usually you have seen that mostly the physical system we are typically going to be discussing is a gas, right? And let's say you have a system enclosed like this. This is a movable piston. So we are going to be looking, thermody deals with, how the energy works. What is the relationship between heat, work, and energy, how the energy is transferred. And also it looks at the properties, the macroscopic properties, such as the pressure, the volume, the temperature of the gas. These macroscopic properties, not the microscopic level. Just a quick recap on the important terms, not terms, but terms in thermodynamics. Too many T's over there. So here, remember what did we say? We are dealing with the system, right? What is the system in thermodynamics? System is that part of the universe that you're studying. And here, what is the universe we are studying? We are studying the gas. So we can say that this gas which is enclosed in here is basically our system. Okay. And then surroundings is everything outside the system, right? So everything outside it, which we can call as the surroundings. So things outside it are your surroundings, and these guys are separated by a boundary, right? Remember we talked about the concept of a boundary, and boundary is what separates them. Now this boundary could be fixed or it could be movable, like a movable piston. So here you can see this is the boundary between the system and the surroundings. Remember we said boundary may be a conducting boundary, which we call as diathermic, or it can be non-conducting, which we call as an adiabatic boundary, which does not allow the transfer of heat. Before we look at the first law, remember we had discussed in the last class the zeroth law of thermodynamics, where basically if you have two systems, A and B, and these are separately in thermal equilibrium with the third system C here, then A and B are also in thermal equilibrium with each other. So let's say, we separated these guys with an adiabatic boundary, A and B with an adiabatic, which does not allow heat transfer, and A and C and B and C are separated by a diathermic boundary, which allows for heat transfer. So remember we said that because heat transfer is allowed, heat will get transferred from a body at or a system at higher temperature to a low temperature till they attain the same temperature. Okay. So that is what the zeroth law talks about, that there will be a heat transfer from A to C, B to C. And so A and B will attain the same temperature as C, which means finally A and B will be in thermal equilibrium also. They will have the same temperature. So if you remove this adiabatic boundary now, will any heat flow between A and B? The answer is no, because they are in thermal equilibrium. But if you want to know all the details about this zeroth law and all the basic thermodynamics stuff, please watch my earlier video. In this video, we're going to focus on the first law of thermodynamics and the specific heats of a gas. So guys, ready for the first law of thermodynamics? Ta-da, here it is, right? So here is the first law of thermodynamics, which basically, let's read the statement and analyze it carefully. It's very simple. So what does it say? That if some heat is supplied to a system, which is capable of doing work. Work doesn't mean your homework, right? The physics work, right? Where there's a force and displacement. So if some heat is supplied and this guy is capable of doing some work, then the quantity of heat I'm putting in red color, then the quantity of heat absorbed is equal to the sum of the increase in internal energy of the system and the external work done. Note these words, internal energy, but external work done by the system on the surroundings. Okay, so let's, I know it's a very long statement, even though it's the first law, right? It's a long statement. So let's break it down, understand it, right? And see, and you tell me, what is this law based on, right? What is it based on, or what principle is this law based on? Okay, so let's take a look. So what we are saying, again, remember we said our system is this gas. Okay, so we have this gas in a container and which has a movable piston over here. So this is basically our system, and you can say this is our surroundings. Okay, so what we are saying now, the first law is saying that if some heat is supplied to the system, so let's say we heat it up, right? So let's say we supply some heat over here. So you can imagine we are supplying some heat, which, and heat, usually the symbol is Q, capital Q. So I'm saying if some heat is supplied to the system, can all of you see that, right? Heat is supplied, then it is capable of doing some, and the system which is capable of doing some work, then the quantity of heat that you're supplying, right, which is absorbed, is equal to the sum of internal energy, right? Increases, sorry, not just internal energy, increase in internal energy and the external work done. So the heat that I'm supplying to this system is being used for two things: to increase the internal energy of this gas, right? You know, this gas has some internal energy, right? Internal energy, remember, because all the molecules are moving. So there is this internal kinetic and potential energy, we can say. So that is inside in the gas, right? So when you supply some heat, the internal energy can increase. So here we can say the gas contains some internal energy. And if you supply some heat, that could increase. So we can say there will be some change in internal energy. I can write over here delta U. Remember, internal energy we symbolize as capital U. Heat we symbolize as capital Q. Okay. So when you supply this heat, do you agree that there could be some increase in the energy, right? So the energy that you've supplied is being used up by the gas, right, to increase the energy of the molecules, right? We can say the kinetic energy of the molecule. Now, plus, you know, if this piston is movable, so let's say the gas expands, right? Then the piston will move up. You guys agree? So when the gas expands, the piston moves up. And when the piston moves up, the gas is basically applying some force on it. The gas is applying force on it, and it is having some displacement. So can I say there is being some work being done? Work being done by the system, which is our gas, on the piston, so on the surrounding, right? Like piston, because like if you put a weight over here, that becomes like the surrounding. So piston is basically doing some work on the surrounding. So here we can say some work is being done. Some work is done. Do you guys agree? Okay. And that work I can denote as, let's say, delta W. So all of you with me on this? So we'll in fact put the delta symbol everywhere. So we say we give it some extra heat, so some change in heat, right? So I'll put delta Q here, right? There's some increase in energy and some work being done. Okay. Now what is basically the first law saying? Something very simple. It is saying that the heat that you're supplying, the delta Q, very, very easy, very easy. The heat that you're supplying, delta Q, is equal to the increase in energy of the gas, the system, plus some extra work done by it, some external work done by the system. That's it. So the system is taking in some heat and using it for two purposes. Only for two purposes. So first law is saying there can only be two things it can do, right? It may do one of them also, right? So it can, or both of them, but there are only two possibilities. The heat can be used up, because remember, heat is a transfer of energy, right? It's not a form of energy. It's a way to transfer the energy to the system. So when we are heating up the system, it is being used to increase the internal energy, the delta U, plus to do some work. Do you guys agree? Does that make sense? Okay. And in the previous class, we have learned what is the work formula. So let's say the in a gas, if it is applying, it is having a pressure P, right? So we can have this work formula that, let's say there is a pressure P over here. So on this piston, let's say the gas is applying a pressure P, okay? And let's say there is a change in volume. So the piston moves up and there is a change in volume delta V. So in the last class, we had learned that the work done will be, you can see the derivation of that, P times delta V. So I can replace this delta W. So I can say, so we can write the first law like this also. Delta Q is equal to delta U, increase in internal energy plus P delta V. Pressure times increase in volume. Make sense? And now can you guys tell me what is this first law? So as simple as that, right? So the first law expression is heat equal to internal energy plus work done. So or change, right? So change in heat equals change in internal energy plus the work done or change in work done, right? And so delta Q is delta U plus P delta V. Now can you guys tell me what is this first law of thermodynamics? What principle or what concept is it based on? And you have heard of that. It's not that you have not, you may not have heard of the first law of thermodynamics, but this principle you have heard of definitely. So can you guys tell me what is it based on? Very good. The answer is it is simply based on the law of conservation of energy, right? So it's saying the heat energy that is transferred, right, is being used to increase the internal energy plus do some work, because we know that when you supply energy, you can do some work. Plus, this law is telling you not only you can do some work, you could increase the internal energy of the gas also. So it is based on, please write that, very important. You can say first law is based on the simple law of conservation of energy, which you have heard from time immemorial. We have been hearing that energy can neither be created nor destroyed, but it changes from one form to the other. Well, first law of thermodynamics is basically the law of conservation of energy in a disguise, or telling it, expressing it in another separate way, and talking about the system, because mostly we ignore the internal energy. It's saying no, don't ignore that. Don't just think in terms of heat and work. There is also internal energy. Clear? So the concept should be crystal clear to you, and this is the very simple equation. I usually I've written it, and you'll see mostly in the books they write it with delta, right? Sometimes work they just simply write W, but this is definitely change in internal energy, and this is the amount of heat, right, or the change in heat energy supplied. Remember, guys, last time we talked about the sign conventions are very important. So basically, when you apply this first law equation, right, what sign to use, positive or negative? That's very important, especially for the numericals. Okay. So here, what are the conventions that the physics guys have decided on? They said that, when heat is absorbed by the system, so heat, that Q term, when heat is absorbed by the system, they said that we will take it as positive. Okay. When heat is given out by the system, we will take it as negative. So heat absorbed positive, heat given out negative. Work done by the system. So this is where the physics differs from chemistry. In physics, we say work done by the system, right? Because in physics, we're designing machines which will do work, right? So that work done by the system is considered as positive. So here we are talking about the work done stuff, right? And this is considered negative. Okay, work done on the system. Okay, if the system is doing work, positive. If the work is done on the system, like let's say you're pushing the piston, then it is negative. Increase in internal energy, this is simple to remember. Okay, again, let's put in the delta symbols here, right? So delta, and this is the change in internal energy, right? So obviously, if the internal energy increases of the system, we say positive. This makes sense. And this is negative. In chemistry, this part is opposite, right? But I'll not confuse you with chemistry. We are looking at the physics conventions now, and that's what you're going to be using. So we learned delta Q is delta U plus delta W. Now, what formulas of heat do we use, right? Because given in the numericals, these are important. Heat, there are lots of formulas, right? Or change in heat, you can put here delta Q if you guys want, right? So here we can say Q, or basically we are talking about delta Q. That means how much heat you need to add, right? So what are the formulas? This one you have heard or in the previous chapter, thermal properties of matter. You can watch my videos on the specific heat capacity and all. We know mass times specific heat capacity times change in temperature. You guys are familiar. I like to call this formula the MCAT. Okay, MCAT, mass times specific heat capacity, which is amount of heat needed for heating 1 gram or unit mass of the substance by unit degree, by unit rise in temperature. Okay, so this is one formula. Okay, when do we use this formula, ML? Do you guys know when do we use this? So this formula is used, the ML formula is used when there is a change of state. Because in change of state, we know there is no change of temperature. Delta T is zero, right? But heat is being absorbed, like when ice is melting or water is going into steam. Then we use the formula ML. And this is when there is no change of state. So this is the formula when no change of state. But there is a rise in temperature. So how much heat do I need? Okay. Now, do you guys know the difference between this delta Q formula and this one? So what is this N capital C delta T? So this first small c over here, this small c, this guy over here is basically called the specific heat capacity, right? Specific heat capacity, or sometimes just called specific heat, right? Specific heat or specific heat capacity. What is this capital C guy? So normally for a gas, you know, it is more convenient rather than using 1 gram, rather than unit mass 1 gram or 1 kg, we use the unit as 1 mole. Okay. So the small n over here is the number of moles. Note this down, very important. So we can find, last time we were finding the heat by multiplying with the mass. This time we are multiplying with the number of moles. N is the number of moles. And your capital C is the molar specific heat capacity, which means the amount of heat needed to raise the temperature of not 1 gram or 1 kg, 1 mole of the substance, right, by 1 degree Celsius. Okay, so you guys got it? So if they give you in terms of moles, use the NCAT, otherwise use the MCAT. So look at the units and all the data given to you carefully. And as we've discussed, if the heat is absorbed by the system, we will put in that equation the number is positive. If heat is given out, remember to put the number as negative. Heat means we are talking about the delta Q. And these are the different, types of formulas of delta Q that you can be using. Clear? Yeah, in physics, there's another one which is called simply heat capacity, right? Where it is not specific, so that MC becomes 1 C dash or capital C, right? So this is different. This is the one I'm talking about, is the molar, right? Where we are multiplying with the number of moles. Work. Now work you can write as W or delta W, right? Whichever way you wish. So again, I'll just put the delta because we are, just to remember that if some change is happening, right? So the work done, so we can put delta W's over here, or W, whatever you're using in school, doesn't matter. So remember this we have done last time. Work done is very simple formula. Pressure, right? For a gas, the pressure times the change in volume. Okay. So let's say this piston is expanding. The gas is expanding, sorry, not the piston. The piston is moving up, and let's say it is applying a pressure P on the piston. Okay. So pressure applied on the piston is capital P. Okay. And let's say there is an increase in volume. So the piston moves up and there is an increase in volume of delta V. So the simple work formula is P times delta V. Okay. And remember, finally to convert the units into SI units so that you get joules. So P times delta V, the derivation I've done last time. But this formula, when can we apply? Only if the pressure is constant. This is an important thing, right? So you can apply this formula only if pressure is constant. But if you may ask, what if the pressure changes, right? If it's variable, then back to your integration stuff, right? We'll integrate P dV, where P is the instantaneous pressure and dV is the small changes in volume. So here the pressure could be changing, and you have to do that, the boring integration. So you have to calculate all the dWs and then integrate. So this is if pressure is variable. So very important concept. And since last time we talked about, so when you're integrating under P dV, it's basically like finding the area under the PV curve. Okay, so this is a general case, whether it is constant or variable. If you find the area under the PV curve, you basically get the work done. Make sense? Okay, and work done is by the system. Remember, if the system is doing work, then we consider it to be positive. If work is done on the system, it is negative. So which basically means that if the gas is expanding, then is the work positive or negative? See, if gas expands, so write that down. So if gas expands, so for the case of expansion, delta V is greater than 0. right? The change in volume is bigger. Final volume is greater than initial volume. So delta V is greater than 0. So we can say work done is delta W is positive. Clear? But if you have the opposite case of compression, if you have the case of compression, delta V is less than 0. Okay. So the work done is negative. Does this make sense? Because the final volume is less than the initial volume. So delta V, this term will be less than 0. So work done will be negative. Okay, clear? If you have any doubt, please put it in the chat. Trying to make the concepts as easy for you. Okay. Then we have this concept of internal energy, or again, we talk about change in internal energy. That's why we write delta U, because actually you cannot measure what is the internal energy of the body, right? Like what is my internal energy? We measure its change. Okay. So change in internal energy, delta U is NCV times delta T. So we are going to be talking about all this CV, CP today, but I just wrote down the formula. So just to let you know, if you want to calculate the change in internal energy, we'll be discussing this formula where N is again the number of moles. So here your N is the number of moles and your CV is the specific heat capacity or specific heat at, again, molar specific heat here at constant volume. What is the meaning of constant volume? We don't allow the gas to expand. So even though you're heating it, you are keeping it at a constant volume. Then we say you can calculate the change in internal energy using this formula. So I know this is looking similar like the delta Q formula, and we'll discuss why it is similar, right? So why it is looking similar to this NCAT formula, right? NC delta T. Here we have a NCV delta T. Okay, so we'll be discussing that. And how do you calculate the CV? So this we'll be talking more about in our kinetic theory of gases, but just to give you the idea here, because sometimes in the numericals they give it. So CV, your molar heat capacity, molar specific heat capacity at constant volume is basically F times F, where what is your F? F is the degree of freedom of a gas, degree of freedom. And for a monoatomic gas, this value is 3. For diatomic gas, this degree of freedom is 5. For polyatomic gas, so triatomic and all those things, the value is 6. Now you'll say, how do we get this? That all these details we are going to be discussing in the next chapter on kinetic theory of gases. But you just believe this formula that CV you can easily find based on the type of gas. So that's very powerful. Or sometimes they'll give you the degree of freedom. You just substitute it here. Times R. Do you guys know what is R? So R is that famous universal gas constant, right? In that PV equal to that constant, which is basically nRT, number of moles times universal gas constant. You guys are familiar with that, right? Otherwise, you can check in your books. So that's how we get the molar specific heat capacity of the gas. So the advantage is this helps us calculate what is the internal energy change, and you can see it is based on the temperature change, right? So if you know this value, you can easily calculate. Now, internal energy is change in internal energy is basically UF minus UI. And one very important thing, that internal energy is a state function. What does that mean? It means that it only depends on the final and initial state, not on the paths taken. So it doesn't matter if you go this way, or this way, as long as the initial and final is same, the change in internal energy will be the same. And this is a big difference from work and heat, like we discussed in the last class. They depend on the work, on the paths taken. They are not independent of it. You cannot just simply say, oh, like we discussed, that if you come back in a cyclic process, work done is 0, wrong, right? Change in internal energy is 0. You have come back to the same state, but still work could be done. Still heat could be gained or lost. So heat and work are not state functions. Internal energy is a state function. Like pressure is a state function. If you come back, change in pressure is 0. Okay. So internal energy, very important point, is a state function. And as we discussed, the change in internal energy delta U will be counted as positive if it increases and negative if it decreases. Okay. Clear? Again, what is the meaning of internal energy? The energy inside this gas, right? So inside the gas, and again, that is based on the kinetic theory of gas. There is the kinetic energy, rotational kinetic energy, vibrational kinetic energy, translation. All those we just touched upon in the last class, and we will do more details in the next chapter also. Clear? But that is basically the energy. You can think of the particles, the molecules, right? And then work done is the external. This is the internal one. So let's try a couple of questions based on the concepts we have done. So let's say we have 1 gram of 1 gram of water at 100 degrees Celsius is converted into steam at the same temperature. If the volume of steam is so much, find the change in internal energy of the system. Latent heat of steam is given, atmospheric pressure is given. So come on guys, I want all of you to pick up your pen and paper, apply the concepts that we have learned, the first law of thermodynamics, and see if you can solve this. So basically in this question, you can see what has been asked. What has been asked is that find the change of internal energy. So basically they're asking us to find the delta U. So if they're asking you to find delta U, most probably you have to use the first law of thermodynamics. So let's write down that law. So you guys remember the equation. What is the equation of first law? Very simple. Delta Q is delta U plus delta W. That's it. Okay. This term we have to find. Now the question is, how much is the heat supply? How do we calculate that? So remember we had looked at some formulas for heat supplied delta Q. Okay. So see which one will be useful for you. For this question, will you use MC delta T, ML, NC delta T, which one? So if you look at the question carefully, it clearly says that water is being converted into steam. So there is clear change of state. During change of state, we said we will use the M times ML, right? Where this is the specific latent heat, the heat required per unit mass. So we will use ML and see latent heat is given to us L. Do you guys agree? So Q is simple to calculate, and that they have given you per gram also. So, and they have given 1 gram of water. So this is simple, 1 times 2256, which is 2256 joules. So much of heat, delta Q, was supplied to the system. That's clear. Okay. And now to find the change in internal energy, I also need to find the work done so that we can apply into this equation. So what is the delta W? How will you find that? So remember we said we'll use the formula P delta V if the pressure is constant. Otherwise we have to integrate. But here I think they're saying it's at atmospheric pressure. So pressure is given constant. You have to find the change in volume. Do you guys agree? Okay. So what will be the delta V over here? Delta V is final volume minus initial volume. Final volume is given to us 1671 centimeter cube. What is the initial volume? We have been given only 1 gram of water. Water is a liquid. So now we have to use that assumption that, okay, we'll take its average density, which is 1 gram per centimeter cube. So 1 gram of water will be 1 centimeter cube of water, right? If you use density, this is using the density concept. So change in volume, do you guys agree, will be 1670 centimeter cube? Yes or no? Okay. If you multiply this with the pressure, can I get the work done? Substitute it here and we are done. So now how will you find the work done? Just let's plug in the values here. So pressure is given to us in good in Pascal. So in SI units, 1.013 times 10 to the power 5. Okay. Change in volume is given in centimeter cube. So I have to convert it into meter cube. So times 1670 times, every centimeter is 1 by 100th of a meter. So 10 to the power minus 6 over here. Yes or no? Okay. So that will give me the work done in joules because everything I've made it into SI units, right? Okay. So work done is coming out to be how many joules? Check. So multiply that and see 169.17. Or if you want to approximate it, it's around 167 because if you take this as 1. Okay. So that's the work done. So how much will be the change in internal energy? So therefore we can say delta U is going to be delta Q minus delta W. Simple. So easy. So delta Q we know 2256 minus 169.17. So how much are you getting? Check. 2086.83 joules. And that's the answer. Finished. Because energy, so energy will be SI unit in joules. There you go. So that's how you do the question. And see, it's all based on the first law of thermodynamics. Simple. Next question. So again, 1 kg of water, 373 Kelvin, converted into steam at the same temperature. Volume of this 1 centimeter cube of water becomes 167 centimeter cube on boiling. Calculate the change in internal energy if the heat of vaporization is given to you and given the atmospheric pressure. So go ahead and try it out. So one very interesting thing from this previous question was that when water changed its state, even though the temperature remains constant, 100 degrees Celsius, but still there is an increase in internal energy because it is becoming steam, right? So some internal energy plus some work done. Okay. So where was that heat gone? In changing the state, which results in change in internal energy and some work done, right? So don't think, oh, no change in temperature, change in internal energy, zero. Wrong. Okay. So here it did, right? So in this question, that's why we used it on the first law. So this question again, it's based on the similar concept. Basically, what you have to do, again, take the first law. Delta Q is delta U. So internal energy plus change in work done. That's it. Okay. So here again, you can see water is converted to steam. So again, you can see delta Q will be mass times latent heat. Very important, right? ML, not MC delta T. So that's what we'll use here. Now here you have to be a little careful. It is given in calories per grams. This is in kg. So you have to take care of the units. Okay. That is the important thing. And then how do you calculate work done? Delta W, delta work is P delta V, because we are assuming it's given constant pressure, right? One pressure is given. And again, change in volume. See, 1671 minus 1, right? So again, like last time. And so from here, you guys can easily find delta U will be delta Q minus delta W. That's it. So same procedure, only just take care of the units, right? This was given in calories. Okay. So maybe you, because calorie is also a unit, so you can get your final answer in calories. Okay. So if your heat is in calories and the pressure you have to take out, but the work done here, the pressure is in Pascal. So yeah, you might have to convert, and 1 calorie is 4.2 joules. Okay. So or 4.18 joules. So you can do that conversion. You guys know this. 1 calorie is 4.18 joules. So if necessary, you can apply this conversion. Same concept, right? So apply this, and this is just based on first law. After that, it's just calculation. So I just wanted to show you how to do these questions. Let's try the next question. This is interesting. At 0 degrees Celsius at normal atmospheric pressure, the volume of 1 gram of water increases from 1 centimeter cube to 1.091 on freezing. So see, the water is freezing here. What will be the change in its internal energy? Normal atmospheric pressure is given to you and latent heat of melting is given. So try this. Very interesting question. Again, you can see it will be based on first law because change in internal energy. So the whole goal is again to do delta Q equal to delta U plus delta W. Yes or no? Okay. Now guys, tell me what is delta Q? Delta Q, because again, change of state means I have to apply ML, right? MC delta T is for increase in temperature. So will you guys, directly just use this here? How will you do it? So will I say change in heat, the delta Q is ML. So will you guys agree that is it going to be equal to ML, which means mass is 1 gram and your latent heat is given 80 calories per gram. So do you guys agree that this should be 80 calories? Is this the correct answer? Yes or no? See, calorie is also a unit. I'm not talking about SI unit, but look here, when you're freezing something, when water is freezing, is heat being added to the system or taken away? When you're freezing water, are you adding heat or taking away heat? Taking away heat. And we said if heat is taken from the system, minus 80 calories. Heat is taken away. Okay. So heat is not absorbed. Heat is not given to the system. Heat is released. Very, very important. Otherwise, it will become wrong. The sign has to be correct. Sign is very important. That's what I told you. Okay. Next thing. What about the work done? Delta W is P delta V. So pressure is given constant, right? 1.013 times 10 to the power 5 in Pascal. Delta V means change in volume, final volume minus initial volume. You can see that the volume increases. So work done will be positive or negative? Positive, because final volume is bigger than the initial volume. So 1.091 centimeter cube minus 1. And of course, to convert it to meter cube, we have to do this 10 to the power minus 6. So many meter cube. And this is in Pascal. Okay. So see, we are all in the SI unit world. So now this you calculate. So see, work done is positive, but heat supply is negative over there. Sign is very important. So if you multiply and check, you will, I think, get 0.0092 joules. 0.0092 joules. But this is in calorie, this is in joules, so it's up to you. You can multiply this by 4.18 to convert it, or you can divide this by 4.18 to convert it into calories, your wish. So let's say you divide this by 4.18 to convert it into calories, right? So you'll get 0.0022 calories. Now you substitute into the equation. So to find the delta U, so now we'll put in delta Q is simply delta U plus delta W. Simple stuff. Delta Q was how much? Minus 80 calories. You have to put there minus 80. Delta U plus 0.0022. So what will be delta U finally? Delta U will be minus 80 and a minus over there. I think we are getting, is this the correct answer? So what is the meaning of this negative answer? What is the meaning of it? Is it making sense? The internal energy of the water or the ice decreases, right? Of the system decreases. So this is the correct answer, and the negative sign indicates decrease of internal energy. Very, very important. Clear? Very important. So get your concept clear, get your signs clear. Otherwise, you'll make a mistake. You will not get the correct answer. So we have talked about the first law of thermodynamics. Now let's talk about specific heat of a gas, right? So what is the meaning of specific heat of a gas? It is the amount of heat required. So how much heat do I need? So suppose if I have raise the temperature of a unit mass, let's say 1 gram or 1 kg. So let's say we are using CGS unit. So let's say I have 1 gram of the gas. Okay. I want to heat it by 1 degree Celsius. So I have a gas. Okay. Let's say I've taken 1 gram of the gas and I want to increase the temperature. So note here, the increase in temperature delta T, not the actual temperature, the change in temperature, we want to increase heat it by 1 degree Celsius. So then I say the amount of heat supplied is equal to the specific heat. So if instead of 1 gram, you're heating m grams, that's why obviously it will be m times more. Okay. If you increase it to 10 degrees Celsius more, right, rather than 1, it will be delta T times more. See, because if the mass is 1 gram and change in temperature is 1 gram, then Q is equal to C. Otherwise, it is MC delta T. And again, just to be consistent with our notation, we can put delta Q over here. Okay, all of you agree? Simple, right? So amount of heat supplied is proportional to the mass, specific heat capacity, and the increase in temperature. So if I want the expression for the specific heat capacity, what will it be? Delta Q divided by M delta T. So you can get delta Q from this, or you can get the specific heat from this thing. Clear? Now, if we talk about the specific heat of a gas or an ideal gas, what is its value? Right? What is its value? Like we talk about specific heat capacity of water, right? So we say that is high because water is an effective coolant. What about gases? What does their value look like? So let's explore. The answer is actually very interesting. It's not a simple value. It basically depends on the conditions. And that's what we are going to explore. So it's not at all a simple answer. So let's say if you have a gas, let's consider a simple case, and you suddenly compress it. Okay. So case one is you suddenly compress the gas. Okay. Then what do you think is going to happen? So again, see, note, to calculate the specific heat capacity of the gas, we'll use this formula. So let's write it down here on this slide as well. So I'm going to be using this formula, that the C, specific heat, is the change in heat by M delta T. Now, in the case when you're suddenly compressing it, And basically here you're not supplying any heat. So we can say the delta Q is 0. Delta Q 0 means that adiabatic stuff, right? You just did it suddenly, so no heat was, there's no heat transfer over here. In this case, so this is clearly a adiabatic change. Delta Q is 0. So in this case, what is the C value? C basically becomes 0 because the numerator is 0. So specific heat of the gas when suddenly compressed is 0. Okay, let's look at case number 2. When you are heating it and you're allowing this piston to keep on smoothly expanding. So basically what's happening is all the heat is being used for work so that there's no increase in temperature of the gas, right? So all the heat that you're supplying, all the delta Q you're supplying over here is being completely used for work, okay? So that your delta T is 0. So in such a case, what will be the C? C is once again delta Q by MC delta T. Oh, sorry, by M delta T. So heat is supplied here, that's fine, but delta T is 0. So the denominator is 0 or tending to 0, right? So we can say that since delta T tends to 0, C basically is infinite, right? So specific heat of a gas could be 0 under this condition when you suddenly compress it, right? If you heat it and allow it to expand, it can be infinite. So values from 0 to infinite. So it's pretty crazy. Or let's look at another case. When you're heating it and you're allowing it to expand such that the change in temperature is greater than 0. So this was the extreme case where you don't allow for change in temperature, but this time let's say there's a change in temperature. So now what will it be? C is delta Q by M delta T. Now both delta Q is non-zero, this is positive, right? So in this case, this guy is positive, this guy is positive. So here, therefore, C is positive. But suppose you let it expand in such a way that the gas actually starts cooling. So maybe the expansion is fast, it starts cooling. Then what will happen? The denominator will be negative. So in this case, your delta Q is positive, but this guy is negative. So our C is negative. Okay. So basically, specific heat of a gas is a crazy number. It depends on the situation. It can be from 0 to infinity. It could be positive or it could even be negative. So don't jump to a conclusion that it has to be within this range. The range is, basically infinite. Now, because it depends so much on the conditions, right? And it's so crazy. So they said, hey, okay, let's bring some sanity here, right? Let's make it easy. So they said we'll talk about two principles. Right? Not your school principal, but your principal basically means important, like school principal is important. So two principal specific heats of a gas is that, what are they? The molar specific heat, molar means we talk in terms of 1 mole at constant volume. So here the key condition is the gas is kept, let's say, in a closed container, right? A fixed container. So the volume is maintained constant. So the molar specific heat at constant volume is the amount of heat required to raise the temperature of 1 mole of a gas by 1 degree centigrade at constant volume. Okay. And this thing is popularly denoted as capital CV. Why capital? Because it is for 1 mole, right? For 1 gram, we usually use small c. Capital C, we use, this is the typical convention for 1 mole, and this is how you denote it. Similarly, you can have one for constant pressure. So molar specific heat capacity at constant pressure is the amount of heat required to raise the 1 mole of a gas by 1 degree centigrade, same thing, but this time at constant pressure. Here, this is at fixed volume, right? Here, the volume is fixed. Here, the pressure is fixed. So in this diagram, the volume is constant. Okay. In this diagram, the pressure that you're applying on the piston is constant. Okay. So this P is constant. And this molar specific heat of the gas, or molar specific heat capacity, or specific heat, normally we say. So molar specific heat of the gas is denoted as capital C subscript P. Okay. So these are the important ones. Remember CP and CV. Okay. Now the question is, which one is greater, or are they same? What is the relation between CP and CV? So CP versus CV, which one do you think is larger? Because remember, CV means the gas is at constant volume. This is your CV guy. This is your CP guy, where the So here volume was constant. So let's write that down. Here volume is constant. Here pressure is constant. The pressure applied on the piston, so maintained on the gas, since pressure is constant. And here we denote it as Cp. Okay. So now which one is greater and how do we prove it? What do you guys think? See, in both the cases, to make it fair, what are we taking? In both the cases, we are taking 1 mole of the gas. So in both cases, we are taking 1 mole of a gas. In both cases, the change in temperature is how much? We said 1 degree Celsius or 1 Kelvin, right? Basically unit temperature, right? So both, that is common to this. Now, which one do you think you have to supply more heat, here or here? Again, use the first law of thermodynamics. What did that say? That delta Q is delta U plus delta W. Correct? Okay. And this molar specific heats are basically that how much heat you need, right? Per unit mole, right? Per unit degree rise. So which one needs more heat? So let's look at the constant volume case. When the volume is constant, can you guys tell me what will happen to this delta W term? For constant volume, look here carefully. For constant volume, delta V is 0. If delta V is 0, so work done, which is P delta V. So your delta, so work done, which is basically P delta V, is basically 0. So there's no work being done. All the heat is being supplied for internal energy, right? So increase in internal energy. So therefore, we can say that in this case, delta Q is purely equal to delta U, right? It's all being supplied for internal energy. How about this case? So at constant pressure, when pressure is constant, then delta Q is delta U plus delta W. So work is being done, right? There is a change in volume. So work is done. Let's say it's allowed to expand. So therefore, I need more heat because I have to increase the internal energy to change the temperature by 1 degree Celsius and this thing. So do you guys agree that more heat required here? So heat is required here and here. This one needs heat only for the delta U. So clearly more heat, more delta Q here. Therefore, will you guys agree with me? Right? Because the increase in internal energy is basically the same, right? It is how much work being done. Okay. So increase in internal energy is happening in both cases, but there's work being done. So therefore, will you guys agree with me that Cp is greater than Cv? The molar, because 1 mole, why molar? Molar specific heat at constant pressure for a gas, which we are talking about ideal gas, right? Or gas is greater than the molar specific heat capacity at constant volume. So let's look at an example question based on that. Let's say we have 2 moles of nitrogen gas is heated from 20 degrees Celsius to 120 degrees at constant volume. Find the heat supply, change in internal energy and the work done. So how will you calculate it? So let's write down the data. What is given to us? Let's write it down. Come on. Don't be scared. So it is given 2 moles. 2 moles is given to us. So we can say N, which we denote as moles. So N is 2 moles. They have told us it's a nitrogen gas. That means it is diatomic. Okay. What is the change in temperature? 20 degrees to 120. Simple. So delta T is 100 degrees Celsius. 120 minus 20. 100 degrees the change in temperature. Correct. And this is happening at constant volume. So it is given constant volume. They are saying find the heat supplied. Right? Find how much is the heat supplied here. So how will you do this? So we want to find the delta Q. Delta Q, what did we say? We can use this formula. Delta Q is number of moles, molar specific heat capacity at constant volume times delta T. Can I use this? Number of moles times the molar specific heat capacity, right? Which means per unit mole per unit temperature times delta T. That's it. Just apply the formula. But now the question is Cv is not given to us. What is Cv? Cv, remember I told you, let's go back to that formula. So this formula we'll be learning in the kinetic theory of gases that Cv is F by 2 times R, where F is what? F is the uh, degree of freedom. For diatomic gas, what is the degree of freedom? 5. So Cv for any diatomic gas, ideal gas, will be 5 by 2 times R. Clear? So let's put down that value here. So Cv will be, because it is diatomic, so Cv, it is diatomic. So let's write down Cv. So that means the degree of freedom. So it's a diatomic gas. Degree of freedom is 5. So Cv will be F by 2R, which means that is 5 by 2R. Yes or no? Do you guys agree? Now R is that universal gas constant. So now let's go ahead and substitute. It's simple substitution. Delta Q will be NCV delta T. So 2 moles times 5 by 2R times 100. So go ahead and calculate this for me, guys. And what is the value of capital R? The universal gas constant. So capital R is 8.314 joules per mole Kelvin or Celsius, right? Or you can take it to be in calories, 2 calorie per mole Kelvin. This is also often used because it's a very convenient unit, 2 calories, right? A very convenient number. So we can put that over here. So 5 times 2 times 100. So the final answer will be, I'm using this R. So what is the final answer for the heat supplied? 5 times 2 is 10, so 1000. So delta Q is working out to be, it's heat. Let's write it in red color. Delta Q is 1000 joules. Concept is clear how to do it? Simple. Now can you guys tell me what will be the change in internal energy? Okay. Or let me ask you the easier question. How much is the work done? What is the work done? Fast. See, it is at constant volume. If it is at constant volume, since delta V is 0, therefore simply work done is 0, P delta V. Finished. So what will be the change in internal energy? You know, you can apply that first law of thermodynamics, delta Q equal to delta U plus delta V. Right? Delta Q equal to delta U plus delta W. Work done is 0. So therefore, can I not say that the change in internal energy, delta U is directly equal to delta Q, which is equal to 1000 joules. Finished. Delta U, you could have also calculated like this, NCV delta T, but there's no need to do that because work done is 0, right? So delta U can be found out like this also, because you know at constant volume there's no work done. So change in internal energy is same as the quantity of heat absorbed. That is why the internal energy is equal, change in internal energy is NCV delta T because delta W is 0. So we had discussed that Cp is greater than Cv. Okay. So we know this formula that we know that Cp intuitively, because at constant pressure work is being done, here no work done. So Cp is greater than Cv. But there's an important relation which is called Mayer's formula, that Cp minus Cv is our very own universal gas constant. Again, these are the molar, right? For 1 mole. So molar specific heat at constant pressure minus molar specific heat at constant volume equals universal gas constant. Very, very important relation. Please learn this. So if you know Cp, you can easily, if you know Cv, Cv is easy to know, F by 2 times R, you can easily find Cp. Just add R plus Cv. Okay. Now question is, how do we prove this? So we are going to look at the derivation of this very, very important relation, right? So basically in this slide, not only Cp is greater than Cv, there's a very important formula. Cp minus Cv is the universal gas constant. So are you guys ready to prove it? We are going to prove it with our very own first law of thermodynamics. So let's start. So what does the first law say? So we'll start with the first law. Delta Q is delta U plus delta W. Please write that, everyone. You have written the first law. Now we'll talk about, first we'll talk about the constant volume case. It's the easy case. So we can say at constant volume, delta V is 0. So we can say work done is 0. The volume is fixed. So there is no work done. So can I say over here that at constant volume, since there is no work done, it's all the change in energy. right? The internal energy. So what is the definition of CV? The molar specific heat. Can you guys tell me what is the definition of it? So molar specific heat is what? Delta Q divided by N delta T. Right? The amount of heat divided by number of moles divided by the change in temperature. Let's take it to be 1 mole of gas. So we can say let the gas be 1 mole of gas. So if we're taking 1 mole of gas, simply CV is delta Q, the amount of heat by the change in temperature. Do you guys agree? Now, since at constant volume delta W is 0, can I say this term goes out? So can I say it is simply equal to delta U by delta T? Will you guys agree with me? Change in internal energy by change in temperature. This is happening at constant volume. Tell me, is this clear? Now let's look at the case of constant pressure. So this we have done till constant volume. Now we are going to look at constant pressure. At constant pressure, Cp is basically delta Q by delta T. Yes or no? Same thing for 1 mole. But this time I can't say delta U by delta T because there's some work done. Okay. So this time what do I have to do? I have to say that this is going to be equal to delta U by delta T plus some work done delta W by delta T. Correct? Now here you know pressure is constant, so work we can simply do P delta V. So we can bring the P outside, right? So at constant pressure, that makes things easy for us. So we can say this will be delta U by delta T, and the pressure comes out delta V by delta T. So don't take pressure, pressure comes out, right? It's simple. So everybody see till here you have got this. This is our CV term. CV is delta U by delta T and Cp is P delta V by delta T. Check. Now if you compare these equations, so look at this. This is our equation number 1 and this is our equation number 2. If you compare it, you can see one very easy thing. Delta U by delta T is CV. So I can replace this guy with simply CV, right? So looking at equation 1 and 2, so right, using 1 and 2, we can make a very simple thing, replacement. Delta U by delta T, we are going to put as CV. So we can say Cp is equal to Cv plus P delta V by delta T. So see, we are almost there because we have to prove that Cp is Cv plus R. So if somehow magically I can prove this is R, I'll be done. Cp equal to Cv plus R or Cp minus Cv equal to R. Okay, so that is the only part left. So let's write down this expression again. Cp equal to, till now we have got Cp equal to Cv plus P delta V by delta T. Delta means change in volume by change in temperature, right? So now what do we do? Okay. So you guys know that, you know the ideal gas equation, PV equal to nRT. And we have been taking 1 mole of the gas. Okay. So for 1 mole of gas, what is it? So for 1 mole, we can say PV equal to RT. Yes or no? Can I say that? PV equal to RT. Yes. Now let's bring the, now we'll see that here we have a delta V, delta T. Here we have PV equal to RT. So now we'll use the math trick, right? That means this you can write as dV by dt or delta V by delta T. Basically, you're doing a differentiation. Okay. So what if I differentiate both these equations with respect to delta T? So if I say delta PV by delta T is equal to delta RT by delta T. So you guys can think in this terms, or you can think it as dPV by dt. We are doing basically, right, a D capital T. Some books use this notation, some books use delta notation, whichever one is preferable in your school. Both are same thing, right? So you could have done everything in terms of D or delta, basically changes, right? So they are the same thing. Now basically you're doing a differentiation here. Here pressure is constant, so we can bring it out of the differentiation. So P is constant, it will become delta V by delta T. Here Universal gas constant is a constant, definitely. So we can bring it out of the differentiation. And this we know is nothing but 1. So guys, look at it. P delta V by delta T is R. That's exactly what we wanted, right? So if you look at this and this equation, we have proved, therefore, Cp is equal to Cv plus universal gas constant, or we can say Cp minus Cv is equal to R. This is called Mayer's relation, and we have derived it in a very simple way. So basically, the CP is always greater because here work is being done. So that's the intuitive way you can remember. At constant volume, no work is done. So less heat needs to be supplied. So it's a smaller value to raise the temperature of 1 mole of gas by the same 1 degree centigrade. So is this derivation clear to all of you? And the important Mayer's relation is called Mayer's formula, Mayer's relation, Cp minus Cv equal to R. Let's look at a question. Calculate the specific heat at constant volume for a gas. Given specific heat at constant pressure is given to you, R is given to you. So this is a simple question. So basically they have given us the, the specific heat at constant pressure. So they've told us that, guys, Cp is, so use the correct notation, Cp is 6.85 calories. See, they've given us the unit of calorie per mole Kelvin. Okay. And they're asking what will be the Cv. Okay. And we know that Cp minus Cv is equal to R, or we can say that basically Cv is Cp minus R. So can you guys calculate that for me? That's basically what they're asking, right? And they've given you R's value also to make it easy. Now see, this R is given in SI unit, but they have told us that joule is 4.18 joule per calorie, right? So here you can see there's a calorie unit, here R is in SI unit. So we should change R into the calorie unit, okay? So that is one important thing to do over here, that the R you will substitute as 8.31 divided by 4.18. So that I think you'll get approximately approx 2 calorie per mole Kelvin. So that is what you need to substitute here. So it will be 6.85 minus 2. So I think the answer you should be getting is 4.85 calorie per mole Kelvin. Remaining units are the same. This is in calories. If you want it in joules, you guys know 1 calorie is 4.18 joules. So just multiply by 4.18. That's it. Next question, calculate the difference between the two principal. Principal, remember the Cp and the Cv of 1 gram of helium gas at STP, given the atomic weight is given and this is given. So another interesting question. Come on, guys, try it out. So can we simply do this? So look at this question. Should we just simply do like this? They're asking us for the difference in Cp and Cv, right? That's what they're asking us. So can I simply say, hey, I know from Mayer's relation Cp minus Cv is R. R, the value is 8.31. That's the answer. Is that the correct answer? This is wrong. Why is it wrong? Because this Cp and Cv we were telling was for molar, 1 mole. Look what they've given us. For helium, they've asked us for helium gas at STP, fine, standard temperature and pressure, but they have told us 1 gram of helium, not 1 mole of helium, 1 gram. So this would be correct if it is for 1 mole, but they've asked us for 1 gram. So please remember this very important concept this question is teaching you. This is for 1 mole. 1 mole means Avogadro number, right? You guys know what is 1 mole? Avogadro number of molecules, right? Or atoms. So here we are talking about the helium, which is monoatomic. So Cp minus Cv is R. But now how do we calculate for 1 gram? So a lot of books give all these formulas. I don't like to learn all the formulas. Just apply simple unitary method. So this difference I know is for 1 mole. So Cp minus Cv is R for 1 mole. So for 1 mole, the difference is R. Okay. So 1 mole of helium is how much? So we know for helium, 1 mole is equal to the gram molecular mass, which is the gram atomic mass, 4 grams. They have asked us for 1 gram. So shouldn't I just divide R by 4? That's it. So for 1 gram of helium, the Cp minus Cv, so now I'll write small, right? Because this is for 1 gram, this was capital. So Cp minus Cv will simply be R by 4. 8.31 or whatever value given divided by 4. That's the answer. Do you guys agree? Please check. 2.0775, which means 2.08 joule per gram Kelvin. See, this is the important thing. This is no longer moles. It is joule per gram Kelvin. All of you understood why we did that? Is that clear? That is why we got this answer. So what does this last question say? An ideal gas at constant pressure and Cp is given to you. See, Cp is given 5/2R. So they've given us at constant pressure. Gas is kept in a closed vessel of volume given to you at a temperature of 300 Kelvin. Pressure is given. An amount of so much heat energy supplied. Calculate the final temperature and pressure of the gas. So let's write down the data of all the stuff that's given. So ideal gas, you can see Cp is given to us. Cp is 5/2R. Okay. The gas is kept in a closed vessel. Volume is given to us. Volume is 0.0083 meter cube. Temperature, capital T, right, in Kelvin. So temperatures, that's the Kelvin temperature. Pressure in Pascal is given to us. 1.6 times 10 to the power 6 Pascal or Newton per meter square. Okay. Or let's write the same as the question. Okay. Amount of so much heat energy supplied, calculate the final temperature and pressure of the gas. Guys, have they given us the number of moles of the gas? Is the number of moles known? No. But we can use the ideal gas equation, right? PV equal to nRT. This very important equation. We can use that to calculate the number of moles easily, because we can easily get the number of moles, which are going to be, N is going to be PV divided by RT. Can you guys do that for me? Just you have to substitute this value, pressure times that volume, temperature is given, and R you can take the universal gas constant 8.314 or 8.31, right? So put in that value of R, and this is joules per mole Kelvin. That will give you the number of moles calculated. So go ahead and substitute the numbers here. So what will you put? So pressure is 1.6. 1.6 times 10 to the power 6. Volume given to us is 0.0083, which basically means 8.3 times 10 to the power 1, 2, 3. 10 to the power minus 3. Okay. R is 8.31. I'll take it approximately 8.3 times the temperature is 300. So you can see the nice thing here is 8.3 will get cancelled. Okay. So 10 to the power 6 and 10 to the power minus 3, we are left with 10 to the power 3. There are two zeros here, so we are left just with 10. So I think finally we are getting 1.6 times 10 is 16. 16/3. Number of moles is simply 16/3. Please check. Now what does the question say? Now so much of heat is supplied, okay, and it is kept in a closed vessel. So closed vessel means the volume is constant, right? And so much heat is supplied to the gas. Calculate the final temperature and pressure of the gas. Okay. So initially the ideal gas has a specific heat at constant pressure. So those details were given to you, but now it is kept at a constant volume and we need to find the final temperature and pressure of the gas. So if we are working, we need to calculate the heat, right? So much heat is supplied, calculate the final temperature and pressure. So basically here, since it is working at constant volume, we have kept the gas in a closed vessel, which means at constant volume. So do you guys agree I need the CV value? And we know from Mayer's relation, Cp minus Cv equal to R, right? So Cv is equal to Cp minus R. And Cp value is given to us 5/2R. 5/2R minus R. So if you do that, what do you basically get? You will get 3/2R. You see, we have got the Cv value also. So Cv value is known. Now can we find the number of the amount of heat supplied, right? So heat supplied is given to us, but we can write this formula now that the delta Q will be NCV times delta T. Do you guys agree? So this will help us calculate the change in temperature because this is the heat supplied at using the constant volume, since it's enclosed in a constant volume. So we can find this easily. Okay. So go ahead and substitute the values given to you. Delta Q is given to us as 2.49 times 10 to the power 4 joules. Number of moles was 16 by 3. CV, I think, was 16 by 3. This was 3 by 2 times R times delta T. Okay. So you can see the 3 will cancel here. Okay. And this 2 8s are. So basically, we are getting that the delta T is 2.49 or 24900 divided by 8R, 8 times 8.31 or 8.3. So this is the change in temperature. Calculate it for me. Approximately, this is turning out to be 374 point something, which is basically 375 Kelvin. That is my delta T, the change in temperature. So they said calculate the final temperature and pressure of the gas. Can you guys do it? So simple, delta T change in temperature is given, original temperature was given to you at 300 Kelvin. So final temperature will be, so we can say final temperature. Final temperature will be the initial temperature plus delta T. Initial given to you is 300 Kelvin. We found change in temperature is 375, 675 Kelvin. Simple. Okay. And the last part, the pressure of the gas. Now, since the gas was heated in a closed container at constant volume, so can we apply this law, right? Or we can apply that P1 V1 by T1 equal to P2 V2 by T2. But if the volume is constant, it basically becomes your Charles law, right? Since volume is constant, this volume gets cancelled because volume is constant. So we get P1 by T1 equal to P2 by T2, right? And P1 is known to us. P1 is given in the question. This was the original pressure, 1.6 times 10 to the power 6 Pascal. Original temperature given to you was 300 Kelvin. New temperature given is 675. You need to find P2 and you're done. That's it, guys. Calculate it and you're done. So P2 will turn out to be 3.6 times 10 to the power 6 Pascal. So your new pressure will be more and it will be 3.6 times 10 to the power 6 Newton per meter square. So this question was a little tricky because it connected various things, right? It connected your ideal gas equation. You calculate number of moles. From there, you calculate your CV, right? You have to find CV to get your delta T. So you find that change in temperature over here using that formula delta Q is NCV delta T. And then finally, we again applied our gas equation P1 V1 by T1 is P2 V2 by T2. Volume gets cancelled. It's constant, right? Because this is constant volume. So that's it. That's how you get the final pressure. So I hope you enjoyed this class on the first law of thermodynamics, where we did the concept of first law in detail and we looked at the specific heat of a gas or the specific heats of a gas, because you have the two principal ones, constant volume, constant pressure, and we looked at the important Mayer's formula, Cp minus Cv equal to R, the universal gas constant. So I hope all these thermody concepts are crystal clear to you. Next time we'll be looking at more into thermodynamic processes, and then we look at second law of thermodynamics. So keep on learning and do check out the other courses on our website, manochaacademy.com, and our Android app. All the links are given below. As you know, we have courses on physics, chemistry, biology, maths, coding, and artificial intelligence. In our courses, you're going to get live classes, concept videos, quizzes, questions, mock test, and revision notes. So guys, do check it out. It'll be really useful for your exam preparation. You can share it with your friends. All the links are given below. Make sure you've subscribed to our YouTube channel. You can follow us on Facebook, Insta, and X. So stay connected with Manocha Academy and just keep on learning.